Now that we have obtained the vector potential, we move on to the electromagnetic fields. In this section, we discuss the radiation field of a short dipole. Consider a short dipole of length delta L carrying current I and directed along the positive z-axis. For this source, the vector potential has only the z component. The current has only the z component, so the vector potential also has only the z component. We have already obtained A sub z in the form shown here. This expression depends only on r, which is the radial coordinate in spherical coordinates. Therefore, it is more convenient to carry out the differentiation in spherical coordinates rather than in Cartesian coordinates. So, we rewrite the unit vector z hat in terms of the spherical unit vectors. Z hat is equal to cosine theta times r hat minus sine theta times theta hat. As a result, the vector potential is decomposed into an r component and a theta component. The r component is a sub z cosine theta, and the theta component is minus a sub z sine theta. Once this preparation is complete, we can calculate the magnetic flux density by taking the curl of the vector potential. In spherical coordinates, the curl looks complicated in general. However, in the present case, the vector potential has only the r and theta components, and it does not depend on phi. Therefore, many terms vanish, and the magnetic flux density has only the phi component. So, we only need to calculate b sub phi. Now we can calculate the electric field. One way is to calculate it from the vector potential, and another way is to use Maxwell's equations. Since B has only the phi component, using Maxwell's equations is much simpler. The exact results are shown here. An important point is that B contains terms proportional to 1 over r and 1 over r squared, while E contains terms proportional to 1 over r, 1 over r squared, and 1 over r cubed. Now consider the far field where r is sufficiently large, or equivalently, where kr is much greater than 1. In that region, the 1 over r term dominates, and the 1 over r squared and 1 over r cubed terms become negligible. Therefore, the radiation field is approximated by the expressions shown here. In the far field, only E sub theta and B sub phi remain. So the electric field and the magnetic field are perpendicular to each other, and both are perpendicular to the propagation direction. Finally, let us examine the ratio between the electric field and the magnetic field. Since H is equal to B divided by mu, we obtain E sub theta over H sub Fi is equal to omega mu over K. Using K equals omega times the square root of epsilon mu, this becomes the square root of mu over epsilon. This quantity is a constant for a given medium, and it is called the wave impedance. So, far from the source, a short dipole radiates a transverse electromagnetic wave with a very simple field structure.